everyone, to today's colloquium. It's a pleasure to welcome Professor Anders Johansen, visiting us from University of Copenhagen. So Anders got his PhD in 2007 from Heidelberg, and then was briefly a postdoc at ASIAA and then Leiden. And then he was a faculty at Lund Observatory for a number of years, and then he's currently a faculty member at the Globe Institute at the University of Copenhagen. Mm-hmm. And Anders is an expert in planet formation. Those of you in the game will know him for pioneering some of the earliest models of planetesimal formation. But today he's going to be telling us about what happens after that in planet formation and planetary atmospheres. So let's please welcome the speaker.
Okay, thank you, Minkai. Thank you very much, and thank for the invitation to come here. So I have been in Taiwan now for 10 days, and I will go back on Sunday. And during this time, I'll give 5 talks. So I'm really seeing Taiwan here for the first time, and it's really exciting to be here. And I'm learning a lot about this country and about the science that is done here. All right, so I want to talk today about planet formation, and particularly towards some of the new results we have in my group on how we can form rocky planets very fast, and also how this connects to the outgassing of the first atmosphere, and even to possible scenarios for the origin of life. I will have one slide about in the end. A good motivation to study planet formation these days is exoplanets, because of course we know of many exoplanets that orbit around other stars. The first exoplanet was discovered in 1995, and this was awarded the Nobel Prize in Physics in 2019. And today astronomers know more than 5,000 exoplanets. Now this doesn't show all 5,000, it shows just what was the main output of the Kepler Space Telescope that was published, this survey in 2013. And you can see from here, this is the period of the planet in days, and this is the radius of the planet: 1 Earth, 4 Neptune, 10 Jupiter. All I wanted to see here is that there are planets of many different sizes out there, and particularly there are many planets around other stars that have these radii between 1 and 4 Earth radii. Now, there are probably also many planets in this regime, but they are hard to detect with the observational techniques that we are using. Now, another issue with this plot is that the Earth orbit would be 365 days. That's about this sort of the habitable zone here around a solar type star, and you see we don't have that many planets out there. So if you focus in on the habitable zone instead, so now I plot in terms of solar insolation, where 1 is the amount of irradiation that the Earth gets from the Sun, 1.5 is approximately Venus, and 0.5 is maybe approximately Mars. Then you get a whole different picture. Then there are not so many planets out there, particularly when we only plot small planets as we're doing here. This is the effective temperature of the whole star. These are very cold stars, because small planets are easier to detect when they orbit small stars. And you see a sort of a couple of handful of systems here. You see the famous TRAPPIST-1 system, and it has 7 planets orbiting it. 4 of them are in the habitable zone. So 1 is about the distance. 1 is the distance from Earth and the Sun, the same effective temperature as the Earth, right? This is where water can be liquid at the surface. We think that it cannot be more than 50%. Then you get a runaway greenhouse effect, something like Venus. And we think it cannot be less than 50% or 70% below Earth, because at some point it starts to be too cold for water to be liquid at the surface. So it's sort of the habitable zone defined here between something like 0.2 and 1.5. You also recognize Proxima Centauri b here. This is the nearest neighbor in our universe, of course, to the Sun, Proxima Centauri, that has a planet orbiting around it, actually smack in the middle of the habitable zone. So this is all good. These are all exciting planets that could be like Earth, but actually we've not detected any atmosphere around these planets yet. So we don't know what the atmospheres are made of. And this really kind of raises 2 questions that I like to explore from a theoretical point of view: is how to both form small planets, and also what could possibly be in their atmospheres, and what could be the connection to the origin of life. Okay, so planets form as dust grains in protoplanetary disk. That dust grains, ice grains, stick together to form larger and larger bodies. And we start with micrometer-sized dust, or maybe even 100 nanometer-sized dust, that form in supernovae and AGB star. This coagulates then, sticks together to form millimeter, centimeter-sized pebbles. These pebbles here, so this is a millimeter-sized grid. These pebbles are actually made in a lab in Germany. They are made out of micrometer-sized dust aggregates, so they are not like pebbles you find at the beach that are igneous and hard. These are like if you take flour from when you bake and push it together. So this is very fragile pebbles made out of dust. And if you collide 2 of those, they tend to fragment each other and make a dust cloud again, or they tend to bounce. So there are sort of 3 questions that I'm very interested in about planet formation. First is, how do you come from these to planetesimals? Like this asteroid Lutetia here of about 100 kilometers in size. And that's actually not something I will talk too much about today. I'll focus more on the 2 next steps: how do the planetesimals grow to form planets? And finally, like with this twin Earth here that we've drawn, what could be the surface and atmosphere conditions on young, potentially habitable planets, and how do we link this to the planet formation? Yeah. So planets form in protoplanetary disks. I said here are pictures of protoplanetary disk here with the ALMA. And of course, what we're seeing here is not the star itself. We're seeing the thermal emission from cold dust that's orbiting around these young stars here. With a scale bar, I believe that must be 10 astronomical units. So these are approximately the size of the solar system. Yeah, typical size of 100 AU. What we see is the emission from the dust and from the ice, where it has a high opacity, and we're not seeing the 99% gas that's probably there, because hydrogen and helium have very low opacities at those temperatures. Now we can measure the total flux coming from these disks, and then we can measure, we can make a cumulative plot as a function of the evolution stage of the star forming region. So class 0 or rather the evolution stage of the star. Class 0 and 1 stars are typically less than 1 million years old. They are almost newly born stars. And class 2 stars are a few million years old, and they have much more evolved protoplanetary disks. And this is the mass of the dust in Earth masses, log. So 1 Earth mass, 10, 100, 1,000, 10,000. And you take the 50% line here, you see that young stars are surrounded by disks that are 100, maybe up to 1,000 Earth masses of solids. So that's a lot of solids. That's enough to make planets. But you can also see the problem here that after a few million years, this drops by 2 orders of magnitude, maybe down to a few Earth masses. Now, this is not because it turns into planets, all of it. It's probably simply because the dust and the gas is accreted onto the star. Yeah. But it also means that I say here, planet formation is a race against time. That planetesimal formation, so the formation of these asteroids, like this one here, and the subsequent growth to planets must occur within a few million years, when there's still mass left in the protoplanetary disk. Now, we think that this stage is natural. Actually, when you analyze the radiation, how this depends on the wavelengths, you can also derive that these are millimeter, maybe centimeter, maybe 100 micrometer sized dust aggregates. So we think this step is observed here. And the question is then, do they all turn into planetesimals? And this we don't know, because we can't really observe planetesimals around other stars. We can only observe them in our own solar system. As I said, I could speak for an hour about this stage alone, but I actually want to sort of now just go on and talk about what happens here. And the first thing I'm going to do is just explore what if all this dust here, hundreds of Earth mass of dust, would turn into planetesimals. Because that's sort of the classical view of planet formation, that once the dust turns into planetesimals, then the planetesimals collide, and then you form planets over a few 100 million years. The problem is that this works well actually for the terrestrial planets, but it does not work so well for the giant planets of the solar system. The issue is that as a planet is moving, here's a planet that is growing by accreting planetesimals around it. As it's migrating towards the star because of the gravity from the surrounding disk, it wants to accrete, or it should accrete all these planetesimals and grow, but what happens instead as it's migrating is that it scatters the planetesimals in front of it. So you see there are a few planetesimals passing over the orbit here and being accreted, but it's very few. This is a nice paper by Tanaka and Ida, by the way, from 1999, where they point out this problem that a planet that's migrating doesn't really accrete very much. So all of this is in some strange dimensionless coordinates. This is the migration time, this is the gas friction time scale. Here's some dimensionless coordinates some normalized coordinates for the eccentricity and for the inclination. But actually this nice paper by Tanaka and Ida, they give prescriptions for the accretion rate as a function of all these parameters. And in this paper in 2019, together with Bertram Bitch, decided to take this prescription that's an n-body code and put it into a 1D semi-analytical model and see, does this mean we cannot form the solar system? And the answer is yes, it means we cannot form the solar system. So we were very generous. We took like 1,000 Earth masses of planetesimals and put all over the solar system. And then we ran this kind of model on it in a parameterized array. And then we want to form Jupiter, Saturn, Uranus, and Neptune. So here's the distance from the star, 5, 10, 20, 30 AU. Here are the masses, 300, 100, 20, approximately. We can start to try to form Jupiter. Jupiter starts here at 5 AU. And the core is growing, and then it's migrating towards the star, and we end up forming a hot Jupiter, which is okay. We know many hot Jupiters around other stars, but we want to form Jupiter. Yeah. So now comes the real problem with planetesimal accretion. If you start at 10 AU and we want to hit Jupiter here, start at 10 AU, we have more region to migrate over, but then the growth rate is so low. So we're only growing from 10 to minus 3 to 10 to minus 2 Earth masses. And it gets even worse if you start further out. So Jupiter is very hard, Saturn is impossible, and Uranus and Neptune are nearly impossible. Now, what people normally do then is they say, yeah, well, maybe planetesimals were actually smaller, reducing the planetesimal size, then the cross-section for the planet gets a bit larger. But this goes a bit in contrast with the solar system, where asteroids are typically 100 kilometers in size, and also theory tells us that they should be about 100 kilometers in size. So we pointed out in this paper that there's a real problem with forming the solar system with the classical planetesimal-driven model, and actually it confirms what people knew already. And that's also why in our group and in other groups, like a decade ago, we decided that there must be another way to form the planets in the outer solar system, and that way may very well be pebble accretion. So how does pebble accretion work? Well, here's a nice illustration from our annual reviews paper. You have a protoplanet here that has a hill radius here, and now it could accrete either a small planetesimal or an even smaller pebble. Yeah. Now, if you try to accrete the planetesimal, we already know that's very inefficient, right? Because as it accretes the planetesimal, it typically just gets scattered by the protoplanet, and the planetesimal goes on a more eccentric orbit and gets even harder to accrete next time around. Yeah. However, replace the planetesimal by a pebble coming in on the same trajectory as the pebble scatters and moves around the planet. It feels friction from the gas. As it feels friction from the gas, then it loses kinetic energy, and at some point it's lost so much kinetic energy that it gets gravitationally bound to the growing planet. And once it has a net negative energy, it has no choice but to spiral in and to be accreted by the planet. This is what it looks like in an actual hydro simulation that we did back in 2012. We take a small, something like this area here. We don't put the planet into the beginning. This is the disk seen from the side, it's seen from the top. We let some turbulence develop in the midplane of the disk. And then after a while, we put in the planet at this point. And after just a few orbits, the planet has sucked in all the pebbles in this simulation. It's like a vacuum cleaner. And this only works because the pebbles are feeling friction. Without friction, without gas in the background, the pebbles would just be scattered all over the place. So it's a gas friction assisted accretion or enhancement of the cross section. Yep. Okay. Now, before I brag that we can form the solar system via pebble accretion, let me just show you something important. Also, that is that we had to stop pebble accretion at some point. Yeah. And I should also explain this, by the way. Here's a star, and here is we imagine there's a disk around this star, and here's a piece of gas. I just take a little bit of gas out of the simulation and just show you that. It feels two forces via the gravity towards the star that will make it orbit at the Keplerian speed, which is fine. And then it also feels a bit of a pressure gradient force. There's a higher pressure here, higher density, higher temperature here, lower density, lower temperature here. So there's a bit of a pressure gradient force that pushes the other way. It makes the gas orbit a little bit slower than the Keplerian speed. And now this makes the pebbles drift towards the star, because the pebble here feels the gravity that will make it orbit Keplerian, but then it feels the headwind from the slower moving gas. Now, after having been in Taiwan for more than a week, I realized it's also quite windy here, just like in Copenhagen and in Lund. So you also know when you're biking in wind, you're losing energy. And you're slowing down. Now, if you're slowing down in a Keplerian potential, you're spiraling in. So that's the radial drift. But now this is key now also to stopping pebble accretion, because as this planet here is growing and it's accreting pebbles around it, it starts to perturb the density in the protoplanetary disk a little bit. And at some point when the density here is down by 15%, there's a local pressure maximum here. Now if the local pressure maximum, the gas is Keplerian, there's no headwind, therefore you don't drift in anymore, woof, then the pebbles are trapped on the outside and you don't accrete anything onto the planet. And this happens at around, let me see here, it happens at 1 AU, it happens at around 10 Earth masses. This is a lot like Jupiter and Saturn's core, by the way. I'll come back to that point. So this is an important mass. I should also say that this is a bit of simplified illustration. Actually, the mass does move over the gap. It's just that the pebbles have to collide and make fragments and make small dust, and then the small dust moves over the gap, just like we see in this coagulation calculation by Stamler 2023. Planet here, pebbles pile up at the outside of the gap, and they fragment each other and make small dust that passes over the gap and then recoagulate at the other side. So it doesn't mean that nothing is on the other side. It just means that pebbles cannot be accreted by the planet anymore. Okay. Now we can try to make the solar system again. With pebble accretion, now since the growth rates are much higher, we can start further out. We know that planets migrate. By the way, this is why they are migrating. So if you put a planet into a protoplanetary disk, like here, you see that it has a wake behind it That's the gas affected by the planet gravity. It has a wake in front. The wake behind is trying to drag or will drain angular momentum from the planet and make it move to the star, and the wake in front will give it angular momentum and maybe make it move out, but the wake behind actually wins, and overall you get a net inwards migration most of the time at least. Okay, so let's try here and make Jupiter. Let's just sit around here. The small dots are 200,000 years, the big dots are a million years, so we make the core in a million years. We had 1 Earth masses, 1.6 million years. We start to migrate a lot, then we migrate in, then we cross the pebble isolation mass here. So at this point, when we come into around 8 AU or 10 Earth masses, we cannot accrete pebbles anymore. Now this is actually very good. Now we're at 10 Earth masses, that's perfectly good, because now we can accrete gas. Once we stop accreting pebbles, then the atmosphere is cooling down and the gas contracts onto the planet, and you can form a giant planet just like Jupiter. We need to accrete 300 Earth masses of the gas, which is basically what we're doing here. And then at some point, actually, you're stopping to migrate. You just park somewhere here around a Jupiter mass at around 5 AU. That's because the planet starts to make a really deep gap in the protoplanetary disk with its gravity, and that slows down the migration and stops the migration entirely. So therefore, you can actually, with pebble accretion, start something at 25, 30 AU, and then park something nicely out at 5 AU. Okay. All right, that was sort of the outer solar system. So that was to make the giant planets. But if we need pebble accretion to form the giant planets, which I think that we do, then a lot of pebbles are going to pass through the inner solar system also. And there they can do two things. They can form super Earth and they can form terrestrial planets. Let's start with the super Earth. Now, what I showed you before, we actually want a semi-analytical model where we form one planet at a time. Here is an n-body simulation where we have several planets growing. In the inner D region, we start protoplanets here between 0.5 and 3 astronomical units. We let them grow and we let them migrate. You see growth tracks as before. And then we're also putting a pebble flux through the inner part of the protoplanetary disk here. So there are always pebbles to accrete also. But the bodies can also interact with each other and accrete each other here. And this is from Lambrecht et al. 2019, by the way. If you have sort of a nominal pebble flux, then you see that the protoplanets are growing and they're migrating a little bit. And then after 3 million years, the disk is gone, and they're sort of stuck at 0.2, 0.3 Earth masses, which we have here. And if you then run the n-body simulation for 100 million years, these protoplanets collide, and you end up with planets that are around Earth and Venus mass. This is actually classical terrestrial planet formation, boosted by pebble accretion here, but this step is actually classical terrestrial planet formation. So you see that it works. Now, if you take the flux and make it a little bit higher, I don't know, 5/3 times the nominal flux, or 3 times the nominal flux, you see you go faster, you migrate more, and sometimes these tracks stop. That's when planets are colliding with each other inside of the protoplanetary disk. And you end up with a system of 1 to 10 Earth mass super Earth here, sitting here. A little bit more if you have a higher flux. And again, if you run it for 100 million years, you get giant impacts, or you get planetary stabilities in these systems, so that you reduce the number of planets to a few in each system. And this way you can see how the formation of super Earth and the formation of terrestrial planets are actually connected processes that happen sort of different ends of the pebble flux. If you have a large pebble flux, super Earth. If you have a smaller pebble flux, more like terrestrial planets. So with all that in mind, we can now try to match the planet populations that we observe around other stars. So we can start planets, we can make synthetic populations, we pick a random starting time and starting positions of the planetesimals, then we run sort of Monte Carlo simulations, and then we see what comes out. And nicely here, we can, under nominal conditions here, form some super Earths that are sitting here in this region here, so like 1 to 10 Earth masses. We can form giant planets that are pretty close to the star here. So sort of hot Jupiters, super Earth. We get a space here. That's because gas accretion is really fast, so it's very unlikely to be caught between 10 and 100 Earth masses. And then we get some cold gas giants also. But you can also see here that Jupiter and Saturn is always a challenge, and I think that's why any planet formation theory should always be confronted with the solar system first, because there we know planets that are massive and pretty far from the star. And you can also see in here we are not really matching Jupiter and Saturn well. However, if we double the metallicity, now we take 2% pebbles in the gas instead of 1%, and now you see you get a whole different population of cold gas giants here that don't exist here, because now when we double the metallicity, we are growing faster, but it's the same migration rate. Then you end up further out, basically. So then, and you see Jupiter and Saturn become characteristic solutions to the sort of pebble accretion growth, which is sort of that you start something out here and then you grow and then you migrate in. Something that starts early probably ended up in here or maybe even in here. Something that starts late will then end consequently further and further down this line here. So you see Jupiter and Saturn are characteristic solutions to the growth curve. And Uranus and Neptune are not bad. They probably both migrated out a little bit during planetesimal scattering. And if they were sitting further in, we can understand them as objects that were growing. They were reaching 15, 20 Earth masses, which is the pebble isolation mass at their distance. They were about to accrete gas, and then the disk vanished around them, basically. So now the giant planets are sort of natural solutions to the growth problem. We can also see here quickly that here's the water ice line at 0.7 AU. The blue dots have more than 30% water, so these are water planets, or they accrete a lot of ice. And you can actually see that we form Venus and Earth here. They're very easy to form in this case here, but in this case they're also almost 50% water, which is unrealistic. You know, it's 70% water at the surface of Earth, but the overall water content of Earth is only a few hundred or a few thousand ppm. Now we can move the water ice line a little bit further out, as we do here, out to 3 AU if the disk was a little bit hotter, and then we can actually see we form Venus and Earth here that are much more dry. Let me come back to that, but I think the main point I wanted to say here is that, you know, giant planets, we need pebble accretion. Super Earth come automatically, but actually terrestrial planets come automatically out of pebble accretion also. There's no end-body effect in this at all. It's very, very easy to form Earth and Venus via pebble accretion. Now this goes against common knowledge, which says that Earth formed via planetesimal accretion. So the sort of classical view is that terrestrial planet formation starts with planetesimals after the protoplanetary disk is already gone. So it looks something like this. The protoplanetary disk is gone. You have planetesimals started in this simulation at 10⁻⁴ Earth masses. They've been colliding up and forming some terrestrial planets. You see their numbers getting reduced with time. You get giant impacts when they cross each other's orbits, and they clear away all of the planetesimals in the end, and you form terrestrial planets in 100 million years or so. Now this is all good. But I would say the issue with this model is how do you then prevent Earth and Venus from forming already from pebble accretion in the protoplanetary disk? And it turns out people have many creative ways of finding out how to not form Earth via pebble accretion. So people have thought a lot about it. Maybe it's because Jupiter blocked all the pebbles. I will show you later. I don't think this is very realistic. Maybe all the pebbles turn into planetesimals by the streaming ability. Then we have thousands of Earth masses of planetesimals in the solar system, which we don't have. Or maybe the pebbles are simply too small in the inner disk for growth by pebble accretion. So these are all valid points in a certain way, but we took the opposite view in our 2021 paper, and we say, what if the Earth formed via pebble accretion? What kind of model can you do out of that, and what does that tell us? And we think that we learned a lot of interesting things from that. So let's turn to the terrestrial planets then. Again, now it's not Jupiter, Saturn, Uranus, Neptune. Now it's Venus, Earth, and Mars, which you have here. Mercury is not in this model. Mercury is tiny and made almost out of metal and is sitting down here. And we have a different way to form Mercury. Ask me if you want to know the details. So let's just focus on these three planets. Now the interesting thing, again, we see something like in the outer solar system, small further out and large further in. It looks a lot like something growing and then migrating, right? And it turns out you can actually fit the orbits of and masses pretty well. If you start out at 1.6 AU and you grow, and then you have to imagine that Venus comes first, and ends up here, then comes Earth and ends up there, and then comes Mars in the end, and Mars doesn't, just like Venus, just like Uranus and Neptune, Mars doesn't have enough time to grow until the disk is gone. Yeah. Now, those of you who are very alert will see that I'm cheating you a little bit. Actually, Earth should have been 0.6 Earth masses and not 1 Earth mass. In this view, Earth should have been less massive than Venus. But we also know that Earth must have suffered at least one giant impact, or maybe an impact with another planet, because the Earth moon is basically almost free of iron. It's a very, very weird object, and it's most likely that it came out of the Earth's mantle after a giant impact. So we know Earth must have suffered a giant impact. So what if we form a fourth or a fifth terrestrial planet here that we could call Theia? That's what people normally call the object that collided with Earth to form the moon. We also call it Theia here. It fits well. It would sit between Earth and Mars. At some point there would be a planetary instability. Theia would hammer into Earth. Earth would get 1 Earth mass and a fairly large moon of just 0.01 Earth masses. Yeah. So this fits in nicely, but notice that we do need a giant impact here, or a planetary instability. But I also showed you for the super Earth systems we also had planetary instability. So when we are in the inner regions of the protoplanetary disk, collisions between planets is a natural thing to happen. I'm not saying that this didn't happen. I'm just saying that maybe a lot of this was driven primarily by the growth via pebble accretion. Also, you can criticize that this model is made to fit. I played around with the parameters until I found the perfect parameter set to form the terrestrial planets, and that's fine. But then what I did afterwards, then I can vary these parameters a little bit and say how sensitive are we to these parameters. So first of all, we can vary the formation place around 1.6 AU and the formation time, like in the maps I showed you before. And then you get this black line of solution here, this black dots of solution, which is sort of, this is one of the implementations of that, where indeed Mars and Earth and Venus are sitting nicely as characteristic solutions for that parameter choice. I can also say, what if the planetesimals formed everywhere, not just around 1.6 AU, but formed all the way from 0 to several AU? Then I get these green dots here. And they're fine in a way. I can recover Venus, Earth and Mars on the green dots also, but they are not characteristic anymore. In a way you could have a small planet on the inside and a large planet on the outside in that case. There's nothing particularly wrong with that, but it breaks a little bit the idea that things are further in because that they migrated more. I can also change the metallicity. Here's pretty low, 0.33%. Earth needs to be lowered in the growth rate a little bit to not turn into super Earth. If I do more like 1%, you see that the black curve goes above Earth and Venus now, and I get more like super Earth forming. So that's just similar to what I showed you before. Now this is all good, that's a model. Now can we find any evidence from the solar system that points to this model? And we believe we actually can. So the last few years I worked a lot with cosmochemists, people who study meteorites in Copenhagen, and we looked a lot at the isotopic composition of meteorites. And this is a very good way to find out what the Earth could have been made of. Now basically when cosmochemists study meteorites, they will make these kind of plots. And I'm not going to say exactly what epsilon is. Let me just say here's chromium and here's titanium. Now we're studying the isotopes, not the elemental abundances. We're studying the isotopes. 0 means that it has the same isotopic composition of Earth. So Earth sort of by definition sits at 0.0, that's the normalization. Positive means that this body has more of the neutron-rich isotopes and less of the neutron-poor, and vice versa. Here, neutron-poor, neutron-rich, neutron-poor, neutron-rich. Okay, and what always comes out of these kinds of studies is that there are two groups of meteorites in the solar system: those that have neutron-rich isotopes and those that have neutron-poor isotopes. Now, the neutron-rich isotopes are actually coming from the outer solar system. They're coming from what we call carbonaceous chondrites. They are arising from from the outer regions of the asteroid belt. These are characterized by having a high fraction of carbon and water in them, and have probably formed under very cold conditions, definitely outside the water ice line. So these are probably probing the sort of outer solar system. And then what we call non-carbonaceous chondrites, a very bad nomenclature, carbonaceous and non-carbonaceous, CC and NC. What we call non-carbonaceous, they are coming from the inner solar system. They have far less volatiles in them and less carbon. So inner solar system bodies seem neutron poor, and outer solar system bodies seem neutron rich. But notice Earth and Moon. So they are definitely plotting in the inner solar system group. We are in the inner solar system, so why would we not have a similar composition as the meteorite from the inner solar system, but leaning a little bit to the outer solar system? You see this in this system also. This is calcium. This is the mu value of calcium. This is a really small excess of the neutron-rich calcium, and this is the absence of the neutron-rich calcium. And again, you see the carbonaceous group in the outer solar system here, positive. The non-carbonaceous, negative. Earth, Moon, Mars, sitting in the NC group, leaning towards the outer solar system. Yeah. And now you can interpret this in two ways. Either you can say that doesn't mean anything. It means that Earth formed from some planetesimals that happen to have exactly this composition here. We are not finding them in our current meteorite samples because they all formed Earth, and it doesn't really mean anything except that there's a large planetesimal reservoir. There's a third reservoir, so to say, of meteorites that would plot exactly on top of the Earth and Moon. Alternatively, you could say, well, what if it means that Earth formed of 70% of this material and 30% of this material? So Earth always started maybe here at the extreme end here, and then was sort of moving up here as it was accreting. That would mean Earth would have had to incorporate a significant amount of material from the outer solar system. And how could that happen? Drifting pebbles. Yeah, pebbles should definitely drift. So this is a possible proof that Earth could have formed via pebble accretion. Yeah. Now recently at the cosmochemistry lab at the University of Copenhagen, they managed to study silicon isotopes for the first time. Silicon has 3 stable isotopes, 28, 29 and 30. Here's the excess of silicon 30. Obviously silicon is very important because it's one of the most important rock building elements in the mantle. And silicon shows actually a very similar story. Here is the inner solar system. Let's call it red now. The NC group are sitting very strongly here at lacking 30 silicon. The outer solar system has an excess of 30 silicon. You have to get some in-between group here also. So here's not so much a dichotomy. It's more like a transition between these. But again, Earth at 0 lies between here and here. And when you run this model in a pebble accretion mixing model, you get something like Earth needs 70% of this material and 30% of this material. Nicely, you can also see from this one that the solar system seems to evolve its silicon-30 composition with the time. So very early on, these bodies here are actually molten. So the parent body are molten. They have not differentiated, because then we will see only the iron, we will not get the silicon. They are molten, but they will not have hot enough to actually differentiate. So they formed early enough to melt by the decay of aluminum 26, which is a short-lived radionuclide, which melts parent bodies that form early. So they have probably heated to 1,000 Kelvin or higher than 1,000 Kelvin. These have maybe heated by a few hundred Kelvin at most. We know that the ice melted in them and so on, but these have formed far later. So we think these formed within 1 million years, these formed after a few million years, and these have sort of experienced intermediate temperatures. And when you put the temperature range on and you get that into an accretion rate, you get a very nice evolution of the solar system from being neutron poor over being just like Earth around 0 to being neutron rich. So it seems that something happened with time. Now, what about this neutron poor and neutron rich? It turned out it probably has something to do with supernova pre-solar grains. That's all I get. Yeah, yes, okay. Yeah, so it probably has to do with the pre-solar grains. So inside meteorites, you find grains that have formed, some of AGB stars, some of them formed in supernovae. The supernova grains are very enriched in neutron-rich isotopes because the ARP process is going on during the supernova explosion, and the ARP process is driving neutron capture up to very neutron-rich isotopes. So it seems that the outer solar system somehow is enriched in the supernova grains, and the inner solar system somehow lacking these supernova grains, and that's what put this fingerprint of inner and outer solar system, which you can use then to infer something about the formation of Earth. So there's a few views of this isotopic dichotomy. I think everyone agrees that has to do with supernova grains, but there are two models basically. So here's a model from NANE 2019, where they're saying, look, maybe so they say that the supernova rich material is blue and the supernova grain poor material is red. So maybe the blue material came down first, and then it was, as the disk was expanding or accreting and expanding outwards, then the blue material ended up in the outer solar system. Then some of the red supernova depleted material came in the inner solar system, and bam, you have a nice dichotomy here with a neutron poor inner solar system and a neutron rich outer solar system. Now I think there's an issue in that model. I don't understand why the material would fall in on the inner side. I think most star formation simulations, including this formation, will have material falling in further out with time. Here you need material to fall in further in. But in a way, it sort of has an explanation for why you get this dichotomy here. Another version is that we have been working on, which goes back to Trinquier out through 2009, is actually that the whole disk was originally blue composition, so it had the amount of supernova grains that you have in the blue composition. But then, if the supernova grains were sitting partially in the icy mantles of dust grains, then inside of the water ice line, these supernova grains would get released and go into the gas form, and maybe they would be so small that they couldn't reaccrete onto the pebbles. Now this doesn't help you much because the water ice line is within 0.7 AU probably, but if the young star had outburst, FU or Ionis outburst where the luminosity would go up by a factor of 100 or 1,000 temporarily, then the water ice line could get pushed out, maybe even out to 30 AU, and then you can make the whole inner solar system now of red composition. Now this doesn't last forever. At some point the pebbles are going to drift in, and you're going to get a transition in the inner solar system even from red to blue again. And we think that's probably what happened to the Earth, that it was accreting over this time scale here, first the red material and then blue material. Yeah. That's a possibility. This is from a recent paper that just came out this year, where we basically take this kind of model and then we see what happens at 1 AU, and you see you start with very red, that's 0, and 1 is blue. You start with red, and after a few million years you sort of shift over to blue here, and you can see how we can put a lot of meteorite parent bodies on here. We can put this sort of very inner solar system like parent bodies to form early on in this region. Then you get some meteorite parent bodies that form either out here or formed here, and you even get some in between ones that probably formed in this kind of transition zone when the blue and the red were getting remixed as the pebbles were drifting in. Yeah, that was the explanation. Okay, now I showed you that pebble accretion could form Earth. I also showed that there's, let's say that the meteoritic evidence is consistent with that picture. I'm not saying it's not consistent with other pictures, but it's certainly consistent with that picture. Just want to sort of take a step back and say, why should we care? In a way, why should we care whether Earth formed by planetesimal accretion or via pebble accretion? Well, first of all, with planetesimal accretion, Earth forms very slowly, whereas with pebble accretion, forms much faster. I find this very interesting, at least. But secondly, there's actually an implication for our atmosphere and possibly also for the origin of life. That is, if you form Earth via planetesimal accretion, typically it's assumed that the inner solar system is filled with these dried out planetesimals. They've heated so much that they lost all of their water. They're colliding together, Earth forms completely dry, and then it collides with a few icy asteroids. That's sort of the delivery of water to Earth. And that will also deliver the organics that will make carbon and nitrogen as part of our atmosphere. And you see this from Raymond et al. 2004. If you run these kind of simulations, it's very random how much water Earth gets. It could be less than one Earth ocean. 1 to 10, 11 to 100, more than 100. It's not a log normal almost. So then there's no prediction power in this. You say Earth just got its amount of ocean water because it happens to collide with 3 instead of 5 or 6 or 7 icy asteroids, right? So it has a broad distribution and is stochastic. Whereas with pebble accretion, actually the volatiles are delivered via rims on icy pebbles. These are rims that contain ice and rims that contain organic molecules. And as they are raining down, you're not delivering by a few pebbles. You're delivering by a rain or torrent of pebbles. And therefore, the volatile delivery is a calculatable consequence of planet formation. Of course, it depends on the parameters we're putting in, but it doesn't have a stochastic component to it anymore. And this means we can now make actually a predictive model for what comes out of the atmosphere in the pebble accretion picture. So this is called pebble snow. That's what ASIAA named it in 2019. I think that's sort of a nice name. Now, first of all, we should, so basically the water, carbon and nitrogen delivered via pebble snow. The water ice line was probably inside a 0.7 AU. I had that in one of the other plots also. I mean, the Earth formed outside the water ice line, where probably between 30 and 50% of the mass was in the form of ice. So the pebbles that are accreted would have had these icy rims. Now, very crucially, there may be a water ice line inside the envelope of the planet, because as the gas gets compressed around the planet, the temperature goes up. So there may actually be a water ice line on the way down to be accreted by the planet. That's what I'm indicating here, basically, so that the water vapor is lost during the accretion. And then when this happens, you see here's an actual hydro simulation of a planet in a protoplanetary disk. Here's the hill sphere. You see the flows from the protoplanetary disk that go in and then out again. They will then bring along with them the water out. And this is a way by which the Earth doesn't end up with 30 to 50% water, but only with a few hundred ppm. Let me show you how this works. So mass fraction, mass of the planet, Earth ocean is like 200 or 300 ppm of water of the whole Earth. We think probably a lot of Earth's water is inside of the core. That has to do with when there is water inside of here's the magma ocean and here's the core. It's a molten planet here. When the volatiles go into the magma ocean, here you see both HC and N partitioned between the silicate, the molten silicate and the molten metal. And actually both HC and N actually prefer to be 10 times more concentrated in metal than in silicate, so a lot of the water will end inside of the core. That's probably the case for Earth also. A lot of water in the core. Anyway, we're aiming for somewhere between a few hundred ppm and a few thousand, and maybe 1,000 ppm water. Now, when we start our planet, we started dry at 10 to minus 3 Earth masses. Then we are creating icy pebbles in the beginning because it's not hot enough for the water ice line to be in the envelope yet. At some point we reach 0.01 Earth masses, then it gets hot enough for the ice line to appear in the envelope and sublimate away the water, which then is not being accreted anymore. And then we accrete dry from 0.01 Earth masses and all the way up, in this case to 0.6 Earth masses. And you see we're sort of approaching a few thousand ppm, which is nicely in the range of where we should be. So this is the way by which we avoid Earth to become a water planet, simply by the sublimation of a big fraction of the water during the accretion. Now we can do the same game for carbon and nitrogen. So how are carbon and nitrogen delivered to Earth? If you look inside of meteorites, carbon and nitrogen are sitting in organic molecules, not as little bacteria or anything like that, but as simple organic molecules that are carbon rich but also have some nitrogen in them, probably inherited from the interstellar medium. Now, if you take such organic molecules and you expose them to higher temperature, they actually survive more than water does. They survive all the way up to between 300 and 400 Kelvin. Then they tend to fall apart. They tend to pyrolyze and then very volatile molecules come out of them, like methane or CO or something very, very volatile that also gets moved away. The only thing that's refractory of carbon and nitrogen is probably graphite. There's a little bit of graphite in some meteorites also. It sort of burns at 1100 Kelvin. So we can run this kind of model on the carbon and the nitrogen. Let's try with the carbon. We start with a few thousand ppm. We want to get down to somewhere between a few 10 and a few hundred. Why a few 10? This is Venus's atmosphere. If you take all the carbon, 100 bars of CO2, take all that carbon, it gives you a few 10 ppm. But it's probably not enough. We also think that in the core there's probably also 90% of the mass. So we think that Venus probably has a few hundred ppm of carbon. Now Earth, we don't have that level of carbon in our atmosphere. We have a few hundred ppm and rising, I guess, still. But that's because a lot of the carbon on Earth has been buried as limestone inside of the mantle of Earth because we have oceans here. So we think that Venus's atmosphere carbon is probably more representative of what Earth has over its whole mantle and its atmosphere. Yeah, and even that is not enough because there's probably 10 times more inside of the core also. Okay, but then we can start with a few thousand ppm. We want to match this region here for carbon, and when we start to destroy the organics and destroy the graphite, we get down to a few hundred ppm, which is pretty nice. Now carbon has the problem that is also in the core. So how much is in the core, we don't know. Now nitrogen is a little bit different. Nitrogen also wants to partition into the core, but nitrogen doesn't dissolve very well in the magma ocean at all to begin with, so nitrogen likes to outgas. So we can probably think that there's so much nitrogen in the core. Then we can trust that the Earth atmosphere nitrogen is 1 ppm if you divide by the whole planet. Venus actually has nitrogen in its atmosphere also probably up to, when you go over the whole planet, probably 3 ppm. But we think for Earth that a lot of nitrogen has been buried by organic processes. Yeah, so we think that it's a good number between 1 and 3 ppm. It's probably the total nitrogen of Earth. We start with the 10 ppm that's in the meteorites, it's too high, and we run this, and we run down to a few ppm. And this way we can actually show with this pebble snow model that we get a good match both to water and carbon and nitrogen of Earth. So it's a different way to deliver volatiles. Okay. I have a few more slides here that I just want to connect it to the outgassing of the atmosphere. It gets a little bit geochemical now. I don't know how many of you here are comfortable with geochemistry. I'm not comfortable with geochemistry, so maybe I can walk you through some of the most basic equations of the magma ocean geochemistry because it's important to understand what comes out of the magma ocean. And the important point is, let's just go take this one again. Rocky planets melt and differentiate both from giant impact or by pebble accretion. So here we have a molten magma ocean, we have a molten core, we have an outgassed atmosphere. Everything out here is the atmosphere from the protoplanetary disk of hydrogen and helium, which will vanish later, by the way, when the disk vanishes. Now, I already showed you about hydrogen, carbon, and nitrogen that they dissolve in the magma and in the metal. And at some point, when the magma ocean crystallizes from the bottom and up, then they will become outgassed. But we need a fourth volatile, and that's oxygen. And oxygen is very, very important because it determines the whole oxidation state of the atmosphere. It determines whether H2 is H2 or H2O, and whether carbon is CO or whether carbon is CO2. And where does the oxygen come from? You say, yeah, maybe it comes from the water. Yeah, but actually not only from the water. Oxygen sits in so many other things. Silicates, iron oxide, there's also, this is Fe2 plus, here's Fe3 plus, FeO 1.5, not a very nice notation, Fe2O3 maybe a bit nicer. So this is Fe3 plus, this is Fe2 plus. Since Fe3 plus, this is Fe2 plus, and then you have silicon as a carrier. Now silicon doesn't get rid of its oxygen easily, so you can forget about this. This oxygen is gone. It's forget about it. But this is very loosely bound, and this is what determines. So basically, the reaction between Fe2 plus, Fe3 plus, O2 and O2 minus are determining this one here. How much oxygen do you outgas from the magma ocean? And this will determine H2O versus H2, CO2 versus CO. Now the simplest picture of calculating this O2 here is you say, well, there's a chemical equilibrium in the magma ocean between iron and oxygen. So there's iron there, and there's oxygen in the magma ocean, and when oxygen reacts with iron, you get FeO. When this is in equilibrium, it goes equally much in both directions, then there's a certain pressure of oxygen, and that's the pressure of oxygen which you put into these equations here. Yeah? And then you can say, well, Earth has in its mantle 7% FeO, actually. I don't know how many of you who knew that, but there's actually like 7% iron in the Earth mantle, but it's in an oxidized form, so we don't think about it as a metallic form. We think about it as an oxidized form that goes together with the rock. When you have that, when you know this fraction, then you can calculate this equilibrium, you know the equilibrium constant, and then you can calculate the pressure of O2, which is expressed as FO2, that's the pressure in bar. Then geochemists tend to take the logarithm of that, and then they take it normalized to some value called the iron wüstite buffer. This is iron and this is the wüstite. Yeah, so this just means if there was 50% FeO in the melt, then this would be IW, and since we are a little bit lower than that, then we are IW minus 2. We are 2 logarithmic units onto the iron wüstite buffer. Now you can see here why it becomes important, because as a function of what you are outgassing now relative to this iron wüstite, so now we said Earth was minus 2, and then you should be outgassing not so much H2, more H2, not so much H2, you should be outgassing H2 and CO, and not so much H2O and not so much CO2. Whereas if you go to higher and higher oxidation stages and go above the iron wüstite buffer, you can turn it around so that at high values here you outgas. If you're very oxidizing, let's say +4, then you get H2 and CO2 and not so much CO and not so much H2. Now if you calculate Earth today, what comes out of volcanoes, it's not -2, it's not IW -2, it's not reducing, it's actually very, very oxidizing. It's sitting in the +2 to +4 range. So Earth's mantle is super, super oxidizing. How can that be? We said now it should be -2. But it's actually more like at +2. It turns out that this reaction here, when you go to higher and higher pressure in the magma ocean, closer and closer to the core, more and more massive planet, then the equilibrium constant changes in such a way that you get more and more oxygen out. That's what the geochemical experiments tell you. When you get a lot of oxygen out, then you get another reaction here, that FeO can react with O2, a quarter of O2 to make this Fe3+. Yeah. Once you have a lot of Fe3+ in the magma ocean, then you get a ton of oxygen, because this reaction here has much more oxygen than that reaction. So once you have a lot of Fe3+ in the magma ocean, you're moving up to this +2 to +4 regime, which is called the FMQ buffer for some other minerals. And then it has a very, very high O2 pressure. So you can see, although the Earth would actually be at -2, it seems it's been pushed up to this +3 or +4, because Earth has a very high pressure it had a very high pressure in the magma ocean that made a lot of Fe3+, which is not part of this calculation at all. Once you have Fe3+ in the magma ocean, this doesn't hold anymore, and you can go to much higher oxidation states, basically. Yeah. So then you can model that, and then you can do it for various objects here, and you can say as a function of the magma ocean base pressure. So here's the moon at sort of a few gigapascal, Mars at maybe 15 gigapascal, Earth actually at 130 gigapascal. Then you can say, what is then the oxidation state over the magma ocean? If you have very low pressure, then this reaction is unimportant, and you get sort of this -2, you get reducing conditions. But if you have very, very high pressure at the CMB, it's not the cosmic microwave background here, but the core mantle boundary, then you get a very oxidizing conditions. And this is despite of the fact that Earth has 7% FeO. Mars actually has much more oxidized iron in its mantle, but Mars doesn't have much Fe3+. Earth has a lot of Fe3+. So then you get an outgassing atmosphere. Okay, so now we can take our model as we did in this paper. We wrote a series of paper here last year where we connect the formation of the planet to the differentiation of the planet to the outgassing of the atmosphere. And now we can run it for Mars conditions and for Earth conditions. So we start with Mars here. It accretes for 5 million years. Forget about what happens before accretion. Then after accretion, you see that you're outgassing now H2. That's the red one. And you're outgassing CO. And remember that Mars doesn't have a very high, it's pretty reducing conditions in the mantle. So you get these reducing molecules out. Now H2 is not an easy molecule to hold on to because of the XUV barrage of the young sun. The sun has a lot of XUV radiation. The H2 flies off basically. As it does so, in like 50 million years, it takes along with all the water, all the CO and all the CO2. Mars ends up without an atmosphere, which is more or less the case today. Mars has only a tiny atmosphere left. That's probably due to Mars's reducing conditions in the magma ocean that made that it outgassed a reducing atmosphere, which is very, very hard to hold on to. H2 is not easy to hold on to. Earth, on the other hand, here's a nice illustration from Deng 2020. Small objects reducing, more and more bigger objects become more and more oxidizing because of this self-oxidation. Yeah. So when we go to Earth here and we run it with a higher oxidation state, you outgas now water and a little bit of H2. The H2 is lost as here, but there's so little of it that it can't do anything. And also, then it cannot remove the CO2 atmosphere. Here we end up with something like 100 bars of CO2. We obviously don't have that today. Venus has, so we think it's a good Venus model. For Earth, you need oceans to bury the CO2 back into the mantle, basically. Yeah. So Earth experiences mantle oxidation at high pressure, and this leads to outgassing of an oxidizing atmosphere. Okay, so that was sort of all the way from the protoplanetary disk and the dust and the planetesimal formation, and then we form planets and we outgas the atmosphere. And I showed you a little bit about the geochemistry of magma oceans. I just want to say one quick slide here in the end about that it actually has some implications for the origin of life. You may know that people like to think about the Urey-Miller experiment for the origin of life, that it has a reducing atmosphere, H2O, CH4, Na3, H2, and then you run a spark through it, and then you get all kinds of biomolecules out, amino acids and nucleotides and so on and so on. Because under reducing conditions, the elements are very reactive when you don't have any oxygen around. So this would be a sort of Mars conditions early on, but Mars also lost its atmosphere very quickly. It's hard to hold on to H2. It has to be small. That's low gravity, and you will lose it because of the XUV irradiation. Now Earth, on the other hand, are outgassed and oxidizing atmosphere, and then this doesn't work at all. If you add oxygen to this, you're not going to form any biomolecules. When you have lightning on Earth, you form NO instead of N2. You don't form sort of nitrogen bound in biological compounds. Yeah. So the question is in a way whether origin of life has best conditions on small planets. Due to biomolecule production by lightning. Maybe life started on Mars and then was transported here afterwards. But actually, this is what chemists like to work on. Actually, biologists will look at this picture instead. They will say, no, it's fine. You can have an oxidizing atmosphere because you can get locally reducing conditions in these hydrothermal vents. What happens there is that Fe2+, we already met Fe2+ in the mantle, it can actually react with H2O and release H2. This is local. H2 is a great way to make chemical reactions because it's a very reducing molecule. For example, so this is a hydrothermal vent, and when hot water comes in contact with the mantle, you get a lot of different compounds out. But look at it, you get H2 out here. You also get some H2S, which are very reactive molecules. You also get CO2, dissolved from the ocean and down. Now we need a CO2 atmosphere because what can you do under these conditions? When you have a lot of CO2 and a lot of H2, then CO2 and H2 can be combined to form methane. That's actually an energy-releasing reaction. It is kinetically inhibited, but you can accelerate this along with catalysts, and that's basically what life does. Life accelerates chemical reactions by having proteins and enzymes and so on to make reactions faster. And this reaction here gives actually energy out. And this turns out that some of the earliest life we had on Earth were the methanogens that lived under these kind of conditions, and they would have loved a CO2 atmosphere as long as there was an H2O source. And again, H2O gets released from the water. So if atmospheres are primarily oxidizing, both on Earth and around other planets, then this points to this origin of life as a more realistic view. This, by the way, called serpentinization, when Fe2+ and H2O react to form H2. And I don't want to talk much about observations, except that I said in the beginning we don't really have atmospheric measurements of small planets around other stars yet. But it was going to be great when we're going to have them, hopefully in a few years. Maybe the TRAPPIST-1 system will be the place where we're first going to see them, because whether it's reducing or whether it is oxidizing is not only important for understanding theory, it's also an important element in understanding the pathways to the origin of life. And that was what I had to say. Thank you.
We have time for a couple of questions. Anyone stood for the question?
Great talk. And for the terrestrial confirmation, why don't the planets migrate further inward?
Right. It's always a question of time. If they will continue, they could certainly do that. So you can say you could draw a growth track that goes all the way in. That's actually an analytical solution that I derived when I was in Japan once together with Chico Ida. So you can derive this shape. So it's only time that can save you. That is that you're growing pretty quickly, pretty slowly. And if the disk vanishes after a few million years, this is where you end up getting parked. Could also be running out of pebbles. If you run a realistic simulation, you will see that pebbles are not drifting in all the time, but they are drifting so fast that they will actually maybe run out faster than the gas is running out. So that's another option. Of course, then you will still migrate. Then you just migrate as a straight line. Yeah.
While you're on the slide, is there evidence Venus also has a major collision from retrograde?
No, we don't know that. I guess I'm not an expert on that. I think people think it's because of the atmosphere itself, that the thick CO2 atmosphere has some tidal effect with the sun that makes Venus slow down. I think, but I'm not entirely sure. And another problem is we don't have meteorites from Venus. It would be fantastic if we had that, but I guess it's completely unrealistic. You see, we have both for Earth and Mars, right? Obviously, we have Martian meteorites, which is fantastic, and Moon. I mean, this is such a wealth of information we have for planet formation. For Venus, we are probably never going to get it. Although I should maybe also say that actually for both Earth and Mars, we can also study the timescale of forming the core from the hafnium tungsten system. And then it seems that Mars actually forms within a few million years. That seems nicely here. Now it seems that Earth's core formed after 50 million years. That goes completely against what I just said here, except for the giant impact, of course. That if there was a giant impact after 50 million years, that would have reset this hafnium tungsten system. So what we are measuring for Earth as a core formation timescale is not the original accretion, it's actually the giant impact. Now if we could have that for Venus, and learn either Venus formed in 2 million years or in 100 million years, that would be a fantastic piece of evidence also, right?
So based on your model, I mean, so how likely you think that solar system planet, like a giant one or previous to one, will form in situ or suffer,
Yeah.
a large migration?
Yeah, I think that migration is something we can't get around. I think it has to happen. It's the same with the radial drift of the dust and the migration of the planet. I think it has to happen, and I think also when we are seeing, actually this looks a lot like the exoplanet observations also, and I think the fact that we don't have many planets in this regime here, I think is the migration pushing everything in, right? But then you can ask in a way, are there many systems that get stuck? Let me get stuck maybe at this stage here. Are there many systems that get stuck at this stage when the protoplanetary disk is gone, and then they are forced to undergo collisions in the classical way afterwards? It's very hard to say. Also, the presence of Jupiter might affect things. That Jupiter is kind of modifying to what degree pebbles are passing into the inner disk or not, and you want to avoid things from growing up to become super Earth. And sort of staying at the terrestrial planet mass. So I still think there's a potential role for Jupiter here somewhere, or maybe Jupiter and Saturn combined, that they were stopping enough of the pebble flux just to reduce it by half or to a third, enough that Earth didn't form to 3 or 4 Earth masses. And I think that would also have been a complete catastrophe, because once you go up to these Earth masses, you start to accrete gas, hydrogen and helium envelope. And if you can't get rid of that, you get stuck with 1,000 bar of H2 and helium on top, which means that the surface never cools down. Then you get a magma ocean with a hydrogen helium atmosphere above. At least Earth will look completely different if it had grown to 3 or 4 Earth masses. Yeah.
So another question is that you show us some plot of isotope distribution.
Yeah.
And I'm wondering, are these all? I mean. So is there any, say, outer solar system sample return or analysis included here?
Yeah, no, that's actually not here. My understanding is that they need rather big samples in order to study that. I know that people have studied Ryugu, and Ryugu looks like a CI chondrite. Let's see if we can find the CI chondrite. Ryugu looks like one of these bodies here. Now, CI chondrites are the ones that are most primitive, with the highest. They're the ones whose elemental abundance is like the solar photosphere, almost spot on. So we think that CI represent the outermost solar system. We think CI is sort of this blue stuff is CI chondrites, and we think that Ryugu may represent this population also, and it's also the one that typically has the highest concentration of neutron-rich isotopes. Yeah.
But these samples basically are all, say, main belt related. So I mean, main belt asteroid related. How does it compare to other possibilities that, say, a sample return from Stardust mission?
I don't think that they did isotopes on that.
Or other
My impression is a very good question. I don't know, and I would like to. I will go and read about it after this. But I don't think they do it for these sample return missions. I think they need too much material to do the isotope studies. It's my impression. But it's a very good question. Yeah.
I think I heard you allude earlier to Mercury being sort of the odd.
Yeah.
And I wondered if you could speak briefly about.
Okay, let me say about Mercury that Mercury is very, very different from the other planets. Mercury has an iron core that's almost 70% of the mass or more. It also, Mercury has almost no FeO in its mantle, like zero. To me, this means that Mercury is a body that formed, I think all these formed outside the water ice line. I think Mercury is a rare example of something formed inside the water ice line. It means the water was gone completely. That also means that there's no oxygen there to oxidize the FeO, the Fe to make FeO. That means it becomes pure iron. And what we have to me, Mercury represents something that happens on a very high temperatures close to the sun, and that it formed under some elevated conditions. We did a model last year where we did one of these outbursts here. And then when we were cooling down afterwards, when you take a solar composition gas and cool it down, you actually we ran a model like a supernova dust production model. We ran it on sort of cooling down gas around the star. Then we could form very large iron grains, very large iron pebbles. Our claim is then these iron pebbles come together to form iron planetesimals that are then colliding to form this tiny planet at point where I was sitting, 0.3 AU, I guess. and that Mercury is maybe an example really of something that is collisional in a population of very iron-rich planetesimals that formed under very, very different conditions than the three others.
We had Chris Armel here a few months ago give a talk on a similar idea.
Yeah.
Where he formed what's it called? Like embryos from like a dust ring.
Yeah.
And he said like the characteristic size for that was like forming like 10 Earth mass.
Right.
What are the ones in your so small?
Why mine are smaller?
Yeah.
I was reducing the metallicity. Yes, I said it was a model made to fit, right? So I was reducing the metallicity to 1/3%. So this was the way I could avoid them from growing to this size here. Yeah. Now I think pressure bombs is an interesting point. Me personally, I don't think that they're really necessary. I think they could be useful, and we should study them. But I like to study planet formation without pressure bombs. Just to sort of, because I don't really think there are any issues not having pressure bombs. I totally agree pressure bombs could accelerate things up, but I think we can make planets without them also.
Do you think that's a reasonable thing to do to lower?
This metallicity?
Yeah.
Well, we probably have maybe we have to make Jupiter and Saturn and Uranus and Neptune to block part of it. Maybe it's the end of the lifetime of the protoplanetary disk, so the pebble flux is a bit lower. And so on. At least it's a reasonable metallicity. You probably, again, it has 3 parameters. I am happy to admit if you can put the metallicity up and the pebble size down, then you can probably make the same curve. So it is a degenerate problem. I'm just throwing a possible solution here. All I want to convince you of is at least that it's consistent with pebble accretion is consistent with terrestrial planet formation. I'm not saying that it's a unique solution. There are many other solutions out there. And if you push the pebble size sufficiently down, you get stuck at lower masses. And if you put the metallicity is sufficiently down, then you get stuck at lower masses also. So it is a possibility that everything is stuck in the solar system at embryo sizes. I'm just saying there's no reason why it should be that way, right? Yeah.
Okay, well that brings us to the end of the colloquium today. We can continue the discussion outside. Hopefully there's tea and coffee. Anders will be here until tomorrow afternoon, 3 or 4 o'clock. So if you want to catch him, he's in 1108, or you can contact me directly on YouTube. Let's thank the speaker again.